Welcome to Pure Light's educational series. Today, we're going to address fructose enrichment, shallow shell technology, fractionation resin. Today's speaker is Robert Moore, Manager of Sugar and Sweetener Technology. Bob has more than 42 years of industrial experience in the sugar and sweetener field. After graduating from the University of Wisconsin with a degree in chemical engineering, he spent 9 years at Illinois Water Treatment Company in the Marketing Development Group. He was involved in designing and selling decolorization, demineralization, chromatographic separation, and mixed bed polishing equipment to the sugar and sweetener industries. Bob joined Pure Light in 1990 to build the sugar and sweetener resin business. He authored several manuals on using resin in the sugar and sweetener field. He currently provides technical support to all of Pure Light's sales force worldwide. So with that, I will turn the presentation over to Bob.
Thank you, Suzanne. Hello, everyone. I'm Bob Moore, Manager of Sugar and Sweetener Technology for Pure Light, and I'll be presenting our shallow shell technology chromatographic separation resin for use in fructose enrichment in the sweetener industry. We'll start by defining what the needs of the sweetener industry are. Then we're going to define what our SST resin technology is. We'll present the many benefits that SST resins provide. We'll cite the current products and the general applications where they're being used. Based on the success in those applications, we suggest how the structure of SST resins could benefit chromatographic separation. We begin our evaluation with pulse testing of a few of our SST Pure Light chromatographic resins, or SST PCRs, against the most common fructose enrichment resin in use today. After pulse testing, we moved on to simulated moving bed pilot plant testing, comparing our SST PCR resin with the most common fractionation resin in use today, and also comparing them against an improvement upon that resin. Lastly, we offer conclusions of the benefits that SST PCR can offer the sweetener industry for fructose enrichment. In many industries, the sweetener industry has goals for energy reduction, water savings, and increased productivity using the same capital equipment. We want to present how SST resins can support those sweetener industry goals. First, we need to define what our shallow shell technology is. When producing the SST resins, we stop the functionalization step before the bead is fully functionalized, leaving an inert core that consists only of the styrene and divinyl benzene copolymer without any functional groups. The outer shell is functionalized while the inner core is not. Expectation would be that the loss of the functional groups in the core would result in a significant loss of exchange capacity. While there is a reduction of total exchange capacity, a bead with only 60% of the radius functionalized results in a reduction of only 6.4% of the total capacity due to the volume calculation for a sphere. The following short video will explain why a loss of core functional groups actually results in an increase in performance.
Pure Light innovation is impacting industrial water and process applications. To achieve improved softening and demineralization performance, we perfected an advanced resin bead structure. It's called shallow shell technology, or SST. In order for all resin beads to work, they need to be activated. But as we activate each SST bead, our exclusive process leaves the center inactive. Because the center of the bead is inactive, ion exchange cannot happen there. When we compare an SST bead to a traditional, fully activated bead, we effectively eliminate the sites that take the longest to exchange, are the most difficult to regenerate, and are the most susceptible to fouling. When regenerating exhausted beads, SST resins regenerate more quickly and efficiently because regeneration chemicals do not have to penetrate the entire bead. contaminant leakage and fouling by iron, barium, and strontium with SST cations, and organic fouling and silica leakage with SST anions is minimized by the efficiency of regeneration. Typically, with SST resins, you save 20 to 30% on regeneration chemicals with equal or better operating performance, and up to 50% savings in rinse and dilution water. When in service, SST resins have a shorter exchange path. This means that the efficiency of ion exchange is improved, and higher purity water is produced. But what about capacity? Logically, a bead with more active sites must have more capacity, right? Actually, no. Compared to SST, a fully activated bead has more leakage and lower throughput at the same regenerant dosage. Whether your system is co-flow or counterflow, softening or demineralization, SST technology is the solution. The economic results for softening applications are great. The results for demineralization applications are even greater. With research and development facilities worldwide, Purolite is dedicated to customizing solutions to your individual system challenges. Visit Purolite.com to find your local sales representative, discover more information about how Purolite's shallow shell technology will improve your softening or demineralization system, and see why Purolite is your solutions company.
We've been supplying SST resins for over 25 years. The initial application was with an SST cation resin in water softening, which resulted in significant salt savings and lower hardness leakage. When we implemented the cation resin for water demineralization, we saw improved throughput for both the cation and anion resin, since silica leakage from the anion is dependent upon sodium leakage off the cation. Lower sodium leakage produces lower silica leakage and longer runs to the same breakpoint. In the Canadian shale oil fields, produced water is used to push the oil up, and it picks up a large amount of hardness and salts. In the high salt background, hardness can only be removed with a weak acid cation resin. Our SST weak acid resin is used to reduce the amount of acid and caustic needed for regeneration. In lactic acid demineralization, cation removal from the lactic acid on a strong acid cation resin competes with the hydrogen ions associated with the lactic acid. The shell of the SST C80C is highly regenerated and thus produces lower leakage. To further enhance the savings in water demineralization, we developed Type 1 and Type 2 strong base anion resins with similar performance enhancements as with the strong acid cation resin. Lastly, we developed an SST cation resin that can be used ahead of an RO system to increase the RO water recovery and is regenerated using only the RO reject stream. Based on the positive results we achieved in these other applications, we thought the shorter syrup diffusion path length may offer advantages in chromatographic separation. For a 320 micron bead, and based on a 60% shell depth, we could reduce the diffusion path length from 160 microns to 96 microns. Put another way, we could make a 320 micron bead react like a 192 micron bead without the pressure drop restrictions. We expected that the SST features a short diffusion path length, higher osmotic shock resistance, lower shrink swell, higher crush strength, and lower rinse volume should result in improved chromatographic separation performance. To prove out our expectations, we started by running pulse test comparisons in fructose enrichment against the most commonly used 320 micron separation resin in the industry. We ran the first pulse test at a space velocity of 1.2 bed volumes per hour. The blue curve is a pulse of dextran blue dye, which was used to establish that the resin packing was proper. If the blue dye curve had any double humps or extended tail, we would need to repack. This is the fructose-glucose separation curve for the most commonly used separation resin in the fructose industry. We can see that the glucose curve peaked at a height of 74 grams per liter, and the fructose curve peaked at a height of 54 grams per liter. The next pulse test used one of the SST-PCR samples at the same velocity. The SST-PCR glucose curve peaked at 92 grams per liter, while the fructose curve peaked at 75 grams per liter. The next set of pulse tests were done at 5 times the velocity to more closely represent the velocity in a commercial separator. At higher velocity, the curves flatten. The competitive glucose curve now peaked at 44 grams per liter, and the fructose curve peaked at 29 grams per liter. At the same velocity, the SST-PCR glucose curve peaked at 52 grams per liter, and the fructose curve peaked at 40 grams per liter. To verify that the SST-PCR would withstand the osmotic shock of syrup water cycling, we cycled it with 60% syrup, followed by water for over 25,000 cycles, with only a 1% breakage in the later cycles. We also measured the crush strength of the beads before and after cycling. The crush strength before cycling was 807 grams per bead, while after cycling it was 784 grams per bead. This compares to a standard, fully functional separation resin like our PCR 642 calcium form of 362 grams per bead. After positive results in the pulse testing, 2 of our SST-PCR samples were tested against the most common fructose enrichment resin in the sequential simulated moving bed pilot plant. The SSMB pilot plant used a feed of 42% fructose at 60 Brix and 60 degrees Celsius. The column sizes and zone configurations are as shown. This slide shows how one of the SST-PCR separation profiles is spread across the 4 zones of the SSMB. One of the SST-PCR separation profiles is shown in red and orange against the competitive separation resin shown in black and blue. The green and light green curves represent the higher saccharides. We graphed the purity and recovery achieved by the 2 SST-PCR resins compared to the competitive resin at the 3 different water-to-feed ratios of 1.32, 1.5, and 1.75. The red and orange curves shows the fructose recovery in the product stream of the 2 SST-PCR resins at the 3 water-to-feed ratios. The blue and light blue curves show the fructose purity in the product stream of the 2 SST-PCR resins at the 3 water-to-feed ratios. The green and purple curves shows the fructose recovery and purity respectively at the 3 different water-to-feed ratios for the competitive resin. It should be noted that this SSMB was limited in how low they could go in water-to-feed ratio by piping and valve constraints. The table shows the data used for the curves, along with the water consumption per ton of commercial 55 fructose and the amount of resin required to produce a ton of 55 fructose per day. The relative advantage of the SST-PCR resins increases as the water-to-feed ratio decreases. The 2 SST-PCR samples showed a fructose recovery of 93 and 97% compared to 83% for the competitive resin, and a fructose purity of 92.7 and 92% compared to 87.1% for the competitive resin. The SST-PCR resins require only 0.43 cubic meters of resin to produce a ton of 55 fructose, while the competitive resin requires 0.54 cubic meters. This data shows the comparison of the 2 SST-PCR resins against the standard competitive resin at the lowest water-to-feed ratio of 1.32. The data from the previous slide shows that the 2 SST-PCR resins show a 15 to 17% lower water consumption, resulting in evaporation savings. a 12 to 17% higher fructose recovery, resulting in less byproduct recycle back through demineralization and isomerization, and 26% higher resin productivity, allowing for increased production. Since most of the fructose enrichment systems in operation in industry today are continuous simulated moving bed systems, SMBs, a pilot test with one of the SST PCR resins was compared to an improved standard competitive resin on the SMB. The new competitive resin was slightly smaller in particle size at 310 microns. The SMB pilot plant was able to operate at the lower water to feed ratios of 1.2 and 1.0. The data shows that the SST PCR sample provided higher purity, recovery, and productivity at both of these water to feed ratios, and the percent improvement was higher at the lower water to feed ratio. The SST PCR 642 calcium form has been operating for over 5 years and can provide higher fructose purity, higher fructose recovery, higher productivity, lower elution water requirement, and lower raffinate recycle. To learn more about fructose enrichment with our shallow shell technology fractionation resin, you can contact me directly at robert.moore@purolite.com.